I welcome all my dear students of BSc Part first year who have opted physics along with either chemistry or geology and mathematics. I was discussing the second paper of physics in which I started telling you about the Faraday's law of electromagnetic induction. Dear students, I left after the start of first experiment, and I told you that in this particular experiment there is a coil which acts as a closed loop or closed circuit connected with a galvanometer, and along the axis of the coil a bar magnet is made to move. This bar magnet can either be taken towards the coil or it can be taken away from the coil. So what parameters I can change? I can change the velocity of this bar magnet. I can move it fast, I can move it slowly. Secondly, I can change the direction of its movement, mean the north pole is moving towards the coil, the north pole is moving away from the coil. I can change the number of turns in the coil by taking different coils. I can change the area of the coil, that is, I can make a larger area, see, like this. This will be another type of coil having larger area. I can change the number of turns, I can change the area. At the same time, I can change the resistance of the wire which is used in the coil also. So all in all, I can have the following parameters which I can change during the experiment. Number one, velocity of the bar magnet. Number two, polarity of bar magnet. Here polarity means whether the north pole is moving towards the coil or south pole going away. Number of turns I can change in the coil. I can change the area of the coil. I can change the resistance of the coil by taking thicker or thinner wire of the coil. Electrical resistance of coil I can change, and the most important parameter which I can change is pole strength of the bar magnet. This is what in the Faraday's experiment observations were taken. What Faraday did observe was that if this bar magnet is made to move, a deflection occurs in the galvanometer. As soon as the bar magnet is made to move, again listen, a deflection occurs in the galvanometer which is connected to the two ends of the coil, which makes a complete closed path for the free electrons to move. What were the observations? Let us think about that. The deflection is larger if the velocity is increased. It means, suppose I am moving this magnet with a velocity of 2 meters per second and I get a deflection of 20 divisions. Then remember, this deflection will remain 20 until the velocity remains constant. So you must learn. Many students think that as the bar magnet is coming closer and closer to the coil, the deflection keeps on increasing. This is a false concept. Until the velocity of the bar magnet remains constant, the deflection remains constant. Be careful. If I double the velocity, the deflection will be increasing, it will become double. But suppose during the motion, if I accelerate the bar magnet, accelerating the bar magnet means the velocity is continuously either increasing, depending upon the retardation or acceleration. If there is acceleration, the velocity is continuously increasing, and then the deflection will rise, it will continuously increase. So velocity means deflection is proportional to velocity. Deflection in coil is proportional to velocity. Larger is the velocity, more is the deflection. Polarity of the bar magnet. Now come, if north pole is brought close to the coil, suppose the deflection is rightward, then if the same north pole is taken away, the deflection will be leftward. It means the magnitude of deflection depends only upon the velocity, but the direction of deflection depends upon this fact that which pole is being taken towards the coil or taken away from the. So I would like to tell you here, the polarity of the bar magnet becomes important. It controls the direction of, or tells me the direction of, controls direction of deflection. Direction of deflection means direction of current which is produced in the coil. One thing you must learn, that taking north pole closer and then taking south pole closer, they will produce opposite directions of deflection. Number of turns in the coil, again listen, deflection in the galvanometer is proportional to number of turns. It means more is the number of turn in the coil, more will be the deflection for a given bar magnet. Area of the coil, again it is proportional to, the deflection is proportional to the area of coil. More is this area, more will be the deflection in the galvanometer. Resistance of the coil means larger is the resistance, smaller will be the current. There is no need to explain, because larger is the resistance, less current will flow for a given potential difference. Now pole strength of the bar magnet again plays a very important role, and you will see that the deflection is directly proportional to the pole strength. Deflection is directly proportional to the pole strength. What does it mean? It means if I take different magnets of different pole strength, and some of you might be knowing that pole strength depends upon the area of cross section also. So if you consider a bar magnet of larger pole strength, then the deflection will rise in the same proportion. So these are the main 6 observations which were found in this experiment. So what Faraday did conclude in accordance on the basis of these observations, and that is called Faraday's first law of electromagnetic induction. What Faraday did conclude, that whenever magnetic flux associated with a closed circuit varies with time, EMF or current is induced. Whenever magnetic flux associated with a closed circuit varies with time, EMF or current is induced in it. It persists until the flux changes. This is again very important language. It persists until the flux changes. Some students think that suppose I bring this bar magnet very close to this coil and I stop it, then you will suddenly find that the deflection will become zero. Mean it is not important how close the magnet is. It is important that how fast it is moving. Its movement is important. Its closeness is not important. So I hope you learn what Faraday did in his first experiment. He was in the first experiment. We observed that production of the induced current or induced EMF takes place in the phenomena of electromagnetic. And he further said, whenever magnetic field associated with a closed circuit varies with time, EMF induced, it persists until the flux changes. It is called electromagnetic induction. This phenomena was defined as electromagnetic induction. So somebody asks you what is electromagnetic induction, then you should say that whenever the magnetic flux associated with any closed loop or closed circuit changes with time, then there is a generation of current and EMF in the circuit. This phenomena is called electromagnetic induction. Okay, right. So we can now one term I have used, that is magnetic flux. I hope you are very well familiar with the magnetic flux. Magnetic flux is a term which simply defines the dot product of magnetic field and area if for a given closed loop. And dear students, this is also equal the number of the magnetic field lines which is passing through the area. So here if I sketch the magnetic field line diagram, then you can easily understand that as this bar magnet moves towards the closed circuit, more and more field lines will pass through this area. This is the area of the coil. So as this bar magnet is brought closer, the flux will increase. As the bar magnet is taken away, the flux will decrease. So this is what Mr. Faraday told us, that it persists until the change takes place. So it is not important the flux is increasing or decreasing. It is important that it changes. And when the flux changes, whether it is decreasing or increasing, in both the cases you will find that there is an increase in the there is a generation of electromagnetic potential difference or current. Now come to the second point. What second point is? Second experiment. Second experiment is also, in the second experiment, see, if you understand first experiment, okay, there is a magnet, there is a circuit, closed circuit. In the second experiment, there was a closed circuit instead of the bar magnet, but there was a rheostat using which I can change the current through it. This is variable potential. You can either vary this or you can change this resistance. So the magnetic field produced by this coil will change if I can change the current. Okay, I am not showing this variation here. I would like to tell you that this potential difference E is constant, and I am changing the current using this rheostat RH. Okay, now there is another circuit or a coil placed nearby this first coil, connected with the ends of a galvanometer. And what Faraday did, he observed that if the current in this is called primary coil, this is the secondary coil. So if current in P is changed, a deflection is observed. In the secondary circuit galvanometer. This is the second experiment of Michael Faraday, that if this current in the primary circuit or primary coil is changed, then there is a corresponding deflection in the galvanometer. Now you can easily correlate the two experiments. Look, the bar magnet has been replaced by a coil. When I change this current, I am changing the magnetic field. And this is what I do, this is what I am doing when I am making the bar magnet to move close or away. So increasing current means taking this magnet towards, decreasing the current means taking this magnet away. At the same time, increasing the current means increasing the pole strength, or decreasing the current means decreasing the pole strength. Here, if I increase the number of turns, I will get more deflection. If I take smaller resistance of the coil, I will get more deflection. So all parameters of these experiments can be associated in the second experiment also, and you will find that this is the same experiment but performed in a different manner. So this experiment also is associated with the first law. Both these experiments are giving this particular rule, that is called first law of electromagnetic induction. And after observing that how fast this flux is changing, Faraday said that it is the second law. And what is the second law of electromagnetic induction? That in the phenomena of electromagnetic induction, the induced EMF is proportional to the rate of change of flux, rate of change of magnetic flux associated with the circuit. Okay, that is, induced EMF is proportional to rate of change of flux, that is delta phi by delta t, or E equals to some constant delta phi by delta t, and we select the dimensional system in such a fashion that k comes out to be 1, so that will lead to delta phi by delta t. And in the next lecture I will tell you that if I use Lenz's law, then this law can be modified as minus delta phi by delta t. This negative sign is in accordance with the Lenz's law, and this is called the second law of electromagnetic induction. Dear students, now I shall discuss the Lenz's law in my next lecture. I hope you have developed few concepts at least in this particular lecture. See you in the next lecture soon. Thank you.